Welcome back! First new lesson in this new crazy online world. Well, let's just jump straight into it. Now we're jumping ahead, skipping chapter 10, we're jumping halfway into chapter 11 because this is going to be a nice comfortable place for us to start. We're going to be looking at surface areas and volumes of three-dimensional solids. But before we can bring in the fun new 3D shapes, there's a little bit that we need to talk about with two-dimensional polygons. So we're going to do that today. So as you can see there, title of today's lesson 11.3 is areas of regular polygons. And the regular part, that's going to be very important. You're going to need to make sure that you remember we're talking about regular objects today. So let's see what we can do. Now, let's start with a pentagon. Because I could give you a triangle or a quadrilateral, but you can find the areas of those on your own. Not a big deal. That's not new. But a pentagon, this is where things can start to get a little bit more interesting. So let's say we've got this pentagon, and it has a side length of 6 centimeters. Now, because it's regular, you know that all of the sides are going to be congruent, and all of these internal angles are going to be congruent. Since it's a pentagon, we can use Euler's formula to figure out how big each of those angles is going to be. So n minus 2 times 180. For a pentagon, that gives us 540 degrees to work with. So each of these has to be 108 degrees. Now that's going to be helpful for us a little bit down the road. But area of this pentagon is the goal today, trying to find the area of the pentagon. Now there's a handy little formula that I'm just going to go ahead and give you right off the bat that works for any regular polygon. The area of any regular polygon can be calculated as taking 1/2 times the perimeter of the object times its apothem. So we've got a perimeter and an apothem. Now an apothem or apothem, that is going to be a new term here. Don't expect many of you have seen that before. Now the apothem is a segment that goes from the center of a pentagon and is perpendicular to one of the bases, or to one of the sides. So this would be your apothem. And it doesn't matter which side you draw it to, they're all going to be the same. It's the same length no matter where you go. So that's the length that we need to find. If you can find that side length, you've got your area. Because we already know the perimeter, since the side length is 6 and it's a regular polygon, we already know that the area is going to be 1/2 times, in this case, 30 times that apothem value. Whoops. Which means that the area is 15 times the apothem. So now your task is just to figure out what that apothem is, approximate it, get a nice value, and you have your area. Well, at this point you can probably predict how this lesson would normally go during lessons. I'd give it to you and say, all right, off you go, see what you can do. A little bit harder to do that here. So what I'm going to do is I'm going to create a right triangle by drawing what we call a radius. Now a radius is a segment that goes from the center of a regular polygon to one of the vertices. So the apothem goes to the edge and is perpendicular. The radius goes to a vertex. Now because this is a regular polygon, drawing this radius actually has the effect of bisecting this angle. So by drawing that segment, we get a 54-degree angle right in here. And if I were to have drawn both radii, we get this lovely isosceles triangle, which means that you know that the base has been bisected. So each of these is 3. Now with this, you should have enough information to get that apothem. We've got this right triangle down here on the bottom. We know one of the angles is 54 degrees. We know one of the sides, one of the legs of this triangle is 3. We're trying to find the other leg. We're going to use SOHCAHTOA because it's a right triangle, so why would we not? So I'm going to set up a nice tangent ratio. The tangent of 54 degrees, I don't know what that's highlighting, is going to be equal to A over 3. Which means that A is equal to 3 times the tangent of 54 degrees. So we can plug that in to our equation here on the side. We see that the area of our pentagon is going to be 45 times the tangent of 54 degrees. Okay, so we'll pull up a calculator. Now I'm going to use Desmos.com because I don't have my classroom set of calculators with me. But down here we've got a scientific calculator that's free to use, plenty powerful. So we'll just type in, we've got 45, times the tangent of 54 degrees. And we see we've got an approximation. So we know that the area is about 61.94 square centimeters. Hooray! Let's do another example. Get rid of all this. And let's bring in an octagon this time. And I will give you the length of the apothem to be 5 inches. I'm going to go through the entire process again, but I would encourage you at this point to pause the video, see if you can figure out the area for yourself, rounded to the nearest hundredth of a square inch, and see if you got it right. I'm going to do the same thing we did before. I'm going to draw a radius to create that right triangle. It is going to be so valuable because the right triangle means we can do SOHCAHTOA. However, I need to know the measurement of this angle, which is going to be half of one of those internal angles, and for an octagon, that is going to be 67.5 degrees. Again, I'm going through figuring out the internal sum by taking n-2, in this case 6, times 180. So I know that there are 1080 degrees in an octagon. So each of those angles is 135 degrees, and half of 135 is going to give me the 67.5. So that's how I knew what that angle was. Once I know that angle's measure, we can start setting up SOHCAHTOA, figuring out everything we need. Now in this case, since we already know the apothem, what I need is the perimeter, because remember that the area of a polygon is 1/2 AP. Half the length of the apothem times the length of the perimeter. To get the perimeter, I'm going to find this side length, double it to get the side of the octagon, and then multiply it by 8 to get the entire perimeter. So let's get started. I'm going to use another tangent ratio. The tangent of 67.5 is going to be equal to 5 over x. So that x length that I've labeled is going to be 5 divided by the tangent of 67.5. I'm going to double that to get the side length of the octagon, because that was only half. We need the whole thing. So the side length of the octagon is going to be 10 divided by the tangent of 67.5 degrees. And then I'm going to multiply that by 8 to get the entire perimeter. So then the perimeter is going to be 80 over the tangent of 67.5 degrees. I've got the perimeter, I know the apothem, we can get our area. So I can go straight to Desmos. We go 1/2 times the apothem times the perimeter, which was 80 over the tangent of 67.5 degrees. And we get our approximated area of 82.84 square inches. 82.84 inches squared. If you're able to do that on your own, fantastic. That's great. If not, keep practicing. I've got a new worksheet that is going up to Canvas so that you can start working. That's going to be your home fun. And if you would like a little bit more guided practice, or if you have some more questions, like for example, why does this formula work? Where does it come from? I'm going to be putting up another video later this week that goes a little bit more in depth, some more complicated examples, talking about where that formula comes from, why it's used, and how we can trust it, that kind of thing. But yeah, I think that's enough for you to be getting on with. So off to the practice, good luck, and have fun.